I'm going to present the first paper here. My name is Balasubramanian. I've been working with test and verification solutions for the past 3 years. I have around 14 years of experience in the verification domain. Apart from work, I like to play some bass guitar and I enjoy running. So I'm going to present a paper about an automotive case study using a portable stimulus standard. I'm going to present this paper on behalf of Infineon Technology. I'm a consultant working for Infineon Technology. Doesn't work. Yeah. So this diagram shows a simpler view of the SOC that we try to verify. You see there are multiple CPUs there. CPUs numbered from CPU 0 to CPU 5. There are lots of IPs like DMA, SPU, some interconnects, all that. So Infineon's average microcontroller products have a comprehensive on-chip trace solution called multi-core keyboard solution, in short called MCDS. So this MCDS as such is an IP that can trace 3 or 4 trace sources in parallel. Let's say from this diagram, CPU 1 can be routed through one of the multiplexers here called MUX0 to reach the observation block 0. Likewise, another IP, for example, the DMA, can be routed through the MUX0 to reach observation block 0. So now you know the number of IPs present in the number of systems to be traced to the whole SOC, and using this complex multiplexer algorithm, one can trace up to 5 IPs or the CPUs in the whole system. So this is the basic duty that we are trying to integrate and test at the SOC or the subsystem level. So one of the main challenges of integrating this, another input is that all the IP stated here, like the CPU, CMAs, are all verified at the IP level. Some amount of sanity is checked where protocol correctness of the IP or whatever certifications inside the IP is all verified through IP level verification. So at the subsystem of the SOC level, the duty is just to integrate all these IPs together, ensure that there is an end-to-end traffic flowing through one end to verify the integration. That's it. So that is the whole target of the subsystem verification that we're trying to achieve now. So one of the biggest challenges is lots of connections. You can see that there are so many CPUs getting connected to the same MUX. Similarly, so many IPs getting connected to multiple instances of the same MUX. So at a subsystem level or at an SOC level, we should prove that this connectivity is all verified. That's the first challenge. Another one is that the adaptation layer just at the front of the MCDS trace block can either detect a load or store instruction from the CPU or program flow instruction from the CPU, or it can completely trace what is the transaction that's happening across the memory. Say, let's say there is a interconnect in the system, and so many masters are trying to access something in the interconnect. So even that can be traced here. So the duty is to ensure that all IPs go through the MUXes to reach subsequent observation blocks. So that's why end-to-end checking is very important here. So typical subsystem or the SOC level tests, as people would have known that most of them are C-based tests because the memory gets loaded into the data gets loaded into the memory, and these instructions are fetched by the CPU to execute them. So we spend lots of time writing C tests, trying to manage the system resources. See, the multiple CPUs are trying to do the same thing. As a test writer, one has to think in all directions that there isn't any conflict between the code running on multiple CPUs. That's what is a big challenge. Moreover, C code doesn't come with lots of constrained randomness that you would even think about. You can't randomize things from the C word, isn't it? So we were looking at probable tools that could be used to help us in automating all these, randomizing all these C code. So in Infineon, the Perspect tool was already evaluated. Perspect is nothing but a system verifier tool provided by Cadence, and it follows the PSS portable stimulus standard. So we thought we would use this portable stimulus standard Perspect tool to verify the integration and connectivity of the MCDS and the related IPs. The MCDS on different derivatives of the same Infineon Aurix products goes with different number of traces. So it varies based on the number of derivatives there, and the same C code platform can be used across different places like simulation, emulation, and the validation. These all were some of the motives that we thought we would use the Perspect. So this is a simple Perspect-based code that let's start to look at. If you see here, whatever I described in the earlier slide, all the mugs, this Perspect top action just decides what all the trace sources that one needs to send in or one needs to verify to ensure that all the end-to-end paths are verified. Let's suppose that mux 0 is represented by objects_a action, and it has a source field that's already defined inside the base action. So if you see the action POPXA, like the object base, is nothing but a like inheritance, where the source is defined in the OB base, and we constrain that the source is selected among one of the trace sources described above as the MCDS POPX SRC list. So the first part now, that to open up traffic coming into MCDS is true. So towards the end of the same slide, you can see that there is a bidirectional constraint that links whether when the source is one of the CPUs, I get to choose whether I trace the data trace, nothing but the loads and stores of the program trace, or CPUs accessing the external memories, so memory tracing. So that is defined in the last line here, where we get to choose whether the data coming in is either loads of stores or a memory access transaction. A typical Perspect test is nothing but a compound action where simpler basic actions are built in a sequence to form a compound action. This in turn turns into a scenario. We can ensure that all the fields inside the action are used in our implementation to produce random effects. So the first part here is to select the trace source. We did it in the last stage. So now, once the trace source is selected, I need to ensure that I expect that the trace is going to come in that particular port. So I'll ensure that MCDS starts generating some sets of messages, which ensures that the incoming trace is traced. Basically, there was a write to some location, or a read from a particular location, or a particular jump instruction, or a particular discontinuity in the program flow. All can be recorded using these MCDS configurations. The third part now, this is also another action we opened up the traffic. We ensured that once the traffic comes in, there are some messages generated by MCDS. But the prime part is traffic should be generated. You see, that CPU has to execute some set of instructions with some jumps in order to see some messages from the MCDS. So that is what is seen in the third action there. So all these are linked to constraints. You see. So using this particular compound action, we were able to create a scenario where mux 0 selects CPU 0 as one of the trace source, and it programs the MCDS trace registers to enable program tracing, and then we instruct the CPU 0 to execute some set of instructions. This is how a typical test in Perspect world looks like. Since MCDS can trace multiple traces simultaneously, we can go up to a case where we can have 4 actions in parallel, all selecting mux 0, mux 1, mux 2, and mux 3 respectively. So all these actions, when we write implementations to these actions, we can use fields that's defined in the action to produce a similar constraint random effect like a system Verilog or any other tool. So the only benefit with Perspect is that you can do randomization on the C world, where some of the functions that one can write can be called based on the fields defined in actions. One can constrain it, or other ways, one can write custom implementation that randomizes C code using Perspect. Now that the Perspect generates us lots of different constraint random scenarios in the environment, we find that the checking is not adequate. The CPU 0 or the DMA IPs, for example, they are basic blocks where you can verify the functionality of them by, for example, a DMA. If you want to verify it, you can read back the data that was already moved earlier by the DMA. But for MCDS, you can't do that because it's a bit more complicated than that. Because it processes the data coming in, produces a message, adds some compression on top for the debug software to understand it. So what we did for the checking part, there's lots of randomization provided by Perspect, but the checking has to be a bit more stringent to ensure that we find out all the common traces at the integration level. So we reused the E model that was used in the IP level verification just around the MCDS thread. So whatever trace coming in, we are probed at the right points, and the E model would predict what the exact message that will be generated by MCDS based on incoming traffic, and it verifies that the messages generated by the MCDS RTL and the predicted messages are equal. So that's how this part is verified. The next part is the SPA assertion. The mux block is more of a control filtering block. So we have tried to verify this using assertions. So we have used formal verification to document all our assumptions and assumptions into the formal verification world, and we have used the same assertion setup, SPA assertion setup in the Perspect world. So what it does is, when we run Perspect random tests, we often get lots of mismatches, lots of things. So when we debug it, we wanted custom prints on why this mismatch comes and all that. So we wrote a set of assertions that work around the mux, and this helped us find out some of the customer reported problems that are reported. So some of the assumptions in between the mux and the CPU, the handshake between the mux and the CPU, were not correct. So this was one of the key benefits that this checking flow introduced. So now this is continuation to the functional coverage. Perspect generates us list of tests, and Perspect also comes with a set of generation coverage, nothing but spectrum like functional coverage. One can get these coverage right at the time when the tests are getting generated. So even before you go on and debug what is the toggle coverage, you can know that the OTGB and OTGBM wasn't implemented in this diagram, so you wouldn't see toggle on those ports of the IP. Say, let's say the intent is to verify toggle on the boundaries of MUX, MCDS, and the CPU trace interfaces. So this itself, generation itself, will tell us whether we would have got some OTGB coverage or not. So likewise, we can always use the first coverage to check whether the test that we did basically covered all cases or not. So this is how a typical regression flow looks like. So we start with the base PSS model. We generate some tests. Later, we simulate the tests using, we run a big regression with the list of tests that's generated with Perspect, analyze topic coverage. Based on the holes, again, fill in some more randomization using the Perspect setup, update the constraints, rerun it. So if we continue to run this loop, you can see that Perspect brings up the coverage from 0 to 90% very quickly. The topic coverage I mean here. So yeah. So to conclude, a test writer, as a test writer, I don't need to know what my CPU model is or my DMI model is. I could just use whatever model was there at the system level just to write my own test. So it's very easy to write tests with Perspect. That's one great benefit. You can generate hundreds of tests using test tables in Perspect where previously generated coverage continues to grow on. You don't go back on topic coverage numbers being low at some time. So Perspect provides lots of randomization. So we need robust checkers that catch the assumptions or that catches the errors when there is a problem between two interfaces. So that's it. Thanks.